So I called this applications of voltage. Example 1 says this: find the final speed of an electron beam if it is accelerated by 125 volts. There's no external agent, so energy is conserved. So what do I mean by this? These are what we call parallel plates. This and this are two metal plates, and you can charge them, one negatively and one positively. And if you do that, you'll actually have an electric field between these. Which way would the electric field point? Which way would a positive sitting right there want to move if it could? Towards the negative. So the electric field would point, don't write this down, in that direction. One of the really nice things about parallel plates is the electric fields between them are uniform. What does that mean? They're constant. You don't have to use any R's or anything like that. But also, you can start to use parallel plates to apply forces on charges. If we put an electron right here, which way will it be repelled? To the right, because like charges. Okay. If we then cut a slit right here, we can actually design an electron gun. Okay? It's a pretty simple piece of technology. You can fire electrons in a beam. How fast will an electron be traveling? Hannah, is this question asking how much work? No. In fact, anybody have a guess on how we're going to handle this? Conservation of energy. G. I think I can do this. What about the potential energy? So we talked yesterday about voltage. What's a good analogy for voltage? Voltage is kind of like height when it comes to gravitational potential energy. More voltage is kind of like dropping an object from a higher height. So if you kind of turn your head sideways, you can imagine that we're dropping this electron from a height of 125 volts. Negative. 125 volts is the potential difference, the change in voltage. And that this is ground level right here. What's my final potential energy then? I'm going to call that the ground. I'm going to call that 0. Because once it leaves here, there's no external forces pushing on it. It's used up all of that voltage. It's picked up whatever energy it's going to pick up. I guess you can kind of imagine this is a hole dug in the ground, except here's where my analogy breaks down, because in real life, Earth would continue to cause it to accelerate if it was falling into a hole. Man, just pretend it stops accelerating when it gets here. But yeah, that's the ground right there. Okay. Potential energy. Don't write this down, going to use this one. How do you know? Okay. What if I had been mean and given you a distance here? How would you still know? How many charges does this require? How many charges have they given me? So what am I going to use? What's the other one? QV. That equals a half m little v squared. This is the equation that I warned you about yesterday that has a capital V and a lowercase v. So the habit I got into, especially because I write on non-lined paper, my capital V, I put the wings on. Voltage! Lowercase v, I don't. But this is the basics of particle accelerators. There's various ways to accelerate particles, Sophia, but one of them is with parallel plates and charges, because like charges, there you go, easy peasy. Let's get the v by itself, the lowercase v by itself. I think times by 2, divide by little m, square root. Times by 2, divide by little m, square root. Okay. 2. What's Q? It's an electron. Okay. Now, here's where I'm going to be doing a little hand waving. Can I take the square root of a negative? Am I taking a square root? Just put everything positive in here. By the way, it would be a negative charge and a negative voltage, but let's just put everything positive in here. I'm going to put 1.6 times 10 to the negative 19, and the voltage change is 125. M, it's an electron. I know it's 9.11 times 10 to the what? Negative 31. Believe it or not, I was just helping a physics teacher colleague with a question like this yesterday over the phone. And they were getting an answer bigger than the speed of light. What had they forgotten to do? It's easy, even professionals. I forgot this, can't believe I did that. Wrote it, forgot to hit it. You get 6.63 times 10 to the 1, 2, 3, 4, 5, 6. You're going to get a big answer. Electrons move pretty fast because they have such a small mass. Any force will cause them to accelerate and get going pretty fast. 6.63, is that right? Times 10 to the 6th? Meters per second. So in the above calculation, when a particle is accelerated from rest by a voltage, really what we're saying, all of the potential energy turns into kinetic energy. You have to be careful here, though. Don't confuse V with V. Have I mentioned once or twice that we don't have enough letters in the English alphabet? I should have. Okay. It's even more interesting if you're not at rest. This is how you can have a charge go through it repeatedly and continually get it going faster and faster. This is what they do at the Large Hadron Collider. They use magnets, and we'll talk about how that works, to bend the charge in a circle, and every time it hits that electron gun or that proton gun, it gets an extra speed boost. Well, you do that a few 100 million times, and you're going pretty near the speed of light. Of course, relativity starts to kick in, then your mass actually increases and it takes more energy. We're going to ignore all that. An electron already moving at 5 times 10 to the 5th enters a set of accelerating plates. I like this question, like this question, like this question. Find its speed when it leaves the plates. Okay. How am I going to handle this? What's it asking me to find? Velocity or speed? That already suggests a scalar approach. Any thoughts? Conservation of energy, except our initial kinetic isn't going to be 0. This is sort of like you threw an object down from a height, and it also gained some potential energy turned into kinetic. So it's going to look like this. We'll start out with good old KE initial plus PE initial equals KE final plus PE final. And again, we're going to argue that this is the ground. That's the 0 point right there. Mr. Dewick, will the electron slow down or speed up? Because this is more positive. In fact, it's traveling through positive 500 volts. It's going to be a half mv initial squared plus qv equals a half mv final squared. We got two choices. I'll let you folks decide. If you want, we can crunch this, get an answer, and then get the little v by itself, times by 2 divided by m square root. Or we can get the v by itself now, times by 2, times by 2, times by 2, divided by m. I don't care. What do you want to do? First method or second method? First method.
No.
So we're going to crunch that. I don't care if you want to do the second method on your own, see if we get the same thing. Okay? So it's going to be 0.5 m. It's an electron. Its initial speed was 5 times 10 to the 5th. Don't forget the squared, Mr. Dewick. Plus, it's an electron. I'm not going to put the positive or negative in because this is a gain in energy on this side. I want to make sure that it's positive because it has this energy. Or I could make the electron negative and the change in voltage negative. But what I'm saying is this is extra energy that's going to turn into kinetic. I want it on the left side to be positive. What's the change in voltage? 600? 500. That's why there's a delta V in that equation on your formula sheet. That equals mv squared over 2. You know what? This isn't so hideous that I can't try typing this in one line. I think I'm going to. 0.5 times 9.11. Scientific notation, negative 31 times 5. Scientific notation, 5 squared. Plus 1.6. Scientific notation, negative 19 times 500. A half mv squared plus qv. And I get 8.011 times 10 to the negative 17th. That equals mv final squared over 2. Now what? Times by 2? Divide by m? Okay. Or if you don't want to times by 2, yes, you can still divide by 0.5. You know who you are. Times by 2, divide by 9.11. Hey, Mr. Dewick, doesn't the m cancel? Is there an m in everything? Not in the QV. Square root 1.33 times 10 to the 7th, even faster. Right? Roughly 1/20th of the speed of light. Yeah, this is what particle accelerators can do. Oh, so maybe doing it Mr. Dewick's way might have been wiser? I don't know. I'll let you figure that one out on your own. Is that right, folks? That we got?
Yeah.
Yeah. Sorry, let me rephrase that. Is that what most of us who follow the teacher's instructions got?
Yeah.
Yes. Okay. I added something here. It's not in your notes, but what's a good analogy for voltage? It's like height. In this situation, I literally turn my head sideways, especially in situation 1, and I think, oh, it's falling from, and I'll use air quotes, height of 125 volts. All of its potential energy from the 125 volts QV is going to turn into kinetic energy when it hits the ground. Again, ground in air quotes. Although we do actually talk about plugs being grounded. So this is one application of voltage and parallel plates, particle accelerators, which are kind of cool. Example 3 says, prove that another unit for measuring electric field is volts per meter. Well, what were the units for electric field? Newtons per? Okay. What can I break newtons into? F equals what? I guess this is kilogram meters per second squared coulomb. Oh, kilogram, Mr. Dewick. Mm-hmm. So a coulomb, if volts are measured in joules per coulomb, I guess stuff moves diagonally. A coulomb is also a joule per volt. Yeah? Stuff moves diagonally? Okay. I'll stick that in here. Sorry? F equals what? M A. Right? So there's newtons. And then coulombs is also still in the bottom. Okay? So, by the way, I'm going to write this a little bit differently. I'm going to write this as divided by coulombs. Let's do that. Newtons per coulomb. And what did we just say a coulomb was the same as? Joule per volt. So this is going to be the same as kilogram meters per second squared divided by joule per volt. How do I divide by a fraction? It's flip it and multiply. It's multiply by the reciprocal. Are we dividing by a fraction? So this is going to be the same as kilogram meters per second squared times volts per joule. Joule, work. Work is what times what? Newton meter. Oh, what's this? What's kilogram meters per second squared? A force, so units. Newtons times volts over Newton meters. What happens to the newtons? What was I trying to show? That newtons per coulomb is equal to volts per meter. Another way of measuring electric field, you have that equation on your formula sheet, although you're not going to use it because I didn't do parallel plates. But if you look, it's sitting right here. Electric field is volts per meter, voltage over distance. We're not going to use this one. Normally I would, but I got to cut corners somewhere. So we've got this one, this one, this one, this one, this one, and this one. Okay. This is newtons. Mass times acceleration. Oh. Right? Oh. Right? I probably could have done this shorter. I haven't derived this one in a while. I normally derive it differently because I've done parallel plates and it pops out of parallel plates quite nicely. Anyways, probably next time I'll do it shorter. How does an older TV work? What I'm talking about are the ones that had that big thing that stuck out the back. You've all at least seen those when you were growing up. Okay? What was back here was what we call a cathode ray tube, a CRT, an electron gun. How can an electron gun make television? With a little bit of cleverness. Are we on the next page over? Okay. So here's what we have. A cathode ray tube. A CRT is a cathode ray tube. A cathode is an electron. They didn't know that when they first named these, but now they do. In the simplest CRT, a beam of electrons is accelerated by one set of plates. I'm going to zoom way in. What we would do is we would charge this very, very negative. We would charge this very, very positive. And although I didn't include it in the picture, don't write this next bit and you can put the charges in. We would also right here put a negative plate, and right here put a negative plate. That would push the electrons towards the center because like charges, okay? And this negative plate would push the electrons forward. You would get a lovely little beam if you cut a little hole right there. This is what a cathode ray tube was. It was an electron gun. Then what? You have a set of deflecting plates. You have one set of plates that's horizontal and one pair of plates that's vertical. So let's look at these horizontal plates. If we charge this positive, which way will the electron get deflected as it comes through here? What if we make this voltage even stronger? Could hit right there. What if we make the voltage weaker? What if we flip the voltage? Basically, we can put an electron wherever we want. Then what we did in old black and white TVs is we painted the inside of the screen with a chemical that would fluoresce when an electron hit it. It would just glow briefly. And that's a television. What? So this is the guts of a TV. Let's look at it in a bit more detail. Put your pencils down, look up.
But there's still something I don't understand, Mr. Whoopi.
Well, what's that, my boy?
I looked real close, and I didn't see any picture going across the room between the camera and the TV set.
But of course you didn't. There wasn't any picture, just electromagnetic waves which are invisible.
But then how...
How does it get to be a picture again? Well, let's go back to the 3D TV. Inside every TV set, there's a big tube. You call it a picture tube. But the correct name is Cathode Ray Tube. It takes the waves from the transmitter and turns them back into electrons. In the back of this tube, there's an electron gun which shoots the electrons at the front of the tube. The front of the tube is coated with a special chemical which lights up when the electrons hit it. And this is what makes the picture.
I get it. The orthicon tube turns the picture into electrons, and the cathode ray tube turns the electrons back into the picture.
Precisely, my boy.
Bit of an older one. Let's look at color TV works. I think this is what I want. Yep.
How does the monitor work? Signals from your computer's video card are loaded into 3 electron guns.
So for color TV, instead of one electron gun like for black and white, you have 3 different guns. One does R, G, and B. One does red, one does green, one does blue. Okay? You've all seen those style of monitors. Those ones were around when you were a kid. We'll talk about how the flat screens work later on today. That's completely different. Uses some cool quantum stuff, but also works. So
at the base of the monitor, there is one gun for each of 3 colors: red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen. Now, these guns don't shoot bullets. Instead, they shoot a powerful beam of electrons towards the face of the monitor. The beams pass through the deflection yoke. It uses magnetism to bend the electronic beams so they can sweep across the entire screen and create the picture we see.
What happens once the beams have swept your monitor? Special chemical phosphors are painted on the inside of the monitor. Energy from the electron beams makes the individual phosphors glow either red, blue, or green, depending on the type of phosphor. The stronger the electron beam, the brighter the phosphors glow. A sheet of metal with holes in it helps keep the electron beams aligned exactly with the phosphors. This is called a shadow mask. The beams sweep across the entire screen 60 times per second.
60 hertz. Modern TVs, newer TVs, some of them are 120 hertz refresh rate. That's 120 times per second. What do movie films broadcast at? How many frames per second when you're in a movie theater? 24. That's enough to already convince your eyes that things are moving and not separate little cells of pictures. Okay?
It happens so quickly that you are unaware of the firing process. Instead, your screen appears to be a steady, continuous image, just as it does now.
But this is why, if you've ever seen sometimes a movie recording of a monitor, the monitor appears to flicker, it's because the movie is taking pictures at a certain frame rate, the iPhone or smartphone, and that frame rate just happens to be really close to the refresh rate of the screen. You're actually seeing the refresh rate. They've almost synchronized, and you can kind of spot it. The workaround is you put a special filter on your camera, and that takes care of it. So that's why in a real movie, when they show a computer screen, you see no flicker. But I'm sure you've seen in YouTube clips or something like, oh, what, is something wrong with all the monitors in that particular room? No, it just so happened that the rate at which the camera was taking pictures and turning that into a seamless video was very, very close to the refresh rate. So let's dive into this in more detail because, you know, TV has raised most of you, right? Okay. Here's a side view of a cathode ray tube and a front view of the screen. So I'd like you to imagine that you are sitting in a chair right here. This is what you're seeing. Here's your TV screen right here. Okay? Oh, this also explains why the old TV screens were curved, right? Now we have flat screens. That was a big, wow, flat screens. That's pretty impressive. So what happens? We send an electron gun from here. When it hits these plates, which are aligned horizontally, it can get deflected up or down. These plates are aligned vertically. It can get deflected left or right. Nick, we can put an electron on this screen wherever we want, just by increasing or decreasing the voltage in either of these plates. Is that all right? So, where will the electron dot end up? Choose from location A, B, C, D, or E. If we make the deflecting upper plate, this one, positive. So before we turn, oh, have any of you seen an old TV? This is why when you first turned them on, there was a big white dot in the middle of the screen. It took a while for everything to warm up, okay? So we're going to start out like that. If we charge this one here positive, where will the electron beam end up? A, B, C, D, or E? Why A? Unlike charges attract, okay? So if we charge that up, it'll end up in location. What if, go back to 0. What if we make the right plate positive, this one? Where will the electron beam end up? B. What if we make the right plate and the upper plate positive? Got something in my throat. Next page. What if we adjust the original voltage from the electron gun so that the beam is off center? It's actually, when everything is turned off, hitting right here. Where will the electron dot end up? Choose A, B, C, D, E, F, or G if we increase the deflecting voltage. So right now, we've got the deflecting voltage deflecting it up slightly. What if we increase that voltage? More specific. G. What if we flip the deflecting voltage? Go back to beginning, this picture, and flip the deflecting voltage. Where will it end up? What if we increase the accelerating voltage so the electrons are traveling faster? If they're traveling faster, will they get deflected more or less or the same if they spend less time in there? They're going to get deflected less. So we can really control where we want that electron to hit. Let's explain your answer using principles of physics. I think we have. So next page. So how does this explain how an old style black and white TV works? It's pretty simple. So we have a fluorescent paint on the inside of the screen. When it gets hit by an electron, it will glow. How fast the electron is traveling determines whether it glows bright or glows gray dimly or not at all. So this is how you could not only get black and white, but shades. by controlling this voltage, how fast it traveled, and then this voltage allows you to change where it hits. Typically, the old black and white TVs, if you ever get a really, really high-speed camera, you can see this. They would start painting on the left, and they would just paint it like this. And then go back in the other direction. And repeat. How many times a second? 60 hertz. Okay, that was enough to easily fool your eyes. So, by sweeping the Y voltage positive to negative, we can move it up and down. Then stepping the X voltage over each time, just by one step, you move the beam over a tiny bit, up and down. Move the beam over a tiny bit, up and down. Move the beam over a tiny bit, up and down. And that was television. The TV signal turns the cathode ray tube beam on and off as it sweeps the screen. Beam on is a white dot. Beam off is a black dot. Beam partially on is a gray dot. Picture. What's your homework? And then I'll show you a cool video. So you can try number 1. You can try number 2. Number 3 is good. 4 is good. 11 is good. 12 is good. Yeah, I cut and paste. And 13 and 14. I'll give you all of these. But we're done the unit. You can also now do every question on the ultimate review. So, how come when Ronan was touching the Van de Graaff, he didn't get a shock? Okay, this is why they like to use, what's the other word we use for voltage? Potential. This is why they like to use the word potential. The reason Ronan didn't get a shock is very rapidly enough charges entered his body that he was at the same potential as the Van de Graaff, the same voltage. What did I say voltage was similar to? What was a good analogy? Height. If you have flat ground here and flat ground here, will water flow from here to here? Water will flow when there's a change in height. Water will flow downhill. Electricity will flow when there's a potential. That's why they like to use that in the industry. It's a nice analogy. So the reason you weren't getting shocked was you were at the same potential, the same voltage as the Van de Graaff, and current will flow, I'm going to use air quotes, sorry YouTube, downhill. Charges will flow downhill. There was no downhill for them to flow. Okay? How do they inspect high voltage lines? I don't mean the telephone lines. I mean the big ones on the towers that run all the way along the mountains that run. How do they inspect? How do they repair? How do they work on those? A lot of them are in the middle of a forest where there's no easy road access. They do this.
And empowers this white knight on a quest to keep the juice flowing.
I don't give 2 hoots and a holler about flying inside a helicopter. Put me outside. That's where I want to be. On a magic carpet. Back in the late 1800s, there was a gentleman by the name of Michael Faraday. He had a theory that if you enclosed a man in a metal cage and energized that cage at whatever voltage, the man would still live. The voltage would flow around him. I wear a hot suit. It's a 75 75% Nomex for fire retardant and 25% stainless steel thread. And that metal thread means I have a Faraday cage around me. 500,000 volts pass over my body, but I can work without interference from the electricity. As long as the helicopter is isolated from ground, we have the ability to bring ourselves to the same voltage potential as the line, like a bird on a wire.
And that's also why birds don't get shocks when they sit on high voltage lines. Very rapidly, their bodies absorb a tiny bit of charge, but you didn't feel it when you touched the Van de Graaff because it's on the outside of you, it's not in your nervous system, and you're at the same potential. They're very rapidly at the same potential as the power lines. They're just fine. Now, we do have an issue. Birds with larger wingspans can inadvertently complete a circuit between them and the power line next to them, and so large birds are killed by power lines every year, but small birds are perfectly safe, and even large birds don't do that very often. So they've raised, sorry?
Well, when they're heavy and then they're like the 100 meters, right?
That's typically, they're not built that way because wind and things make the lines vibrate. There's enough distance between them, you're not going to get it to sag. In fact, you're going to see this handles the weight of a person pretty easily.
Our pilots are very smooth. It's like they can read our every thought. There's such a hunger for electricity these days. Nobody wants to take lines out of service just to maintain them.
That's a job, though. If any of you are looking for an interesting career and have a pretty good head for heights,
people ask me, do you think what you do is safe? And I say, well, in our operation, everything that we do, every move that we make is thought of and rehearsed before, so it's as safe as crossing the street. It's not a job for a hot dog. There's only three things I've ever been afraid of. Electricity, heights, and women. And I'm married, too.
So there's a neat application of really the Van de Graaff generator writ large, why you didn't get a shock. If you're at the same potential, the same voltage, current charges will not flow between you because charges want to flow downhill. Or you're at the same energy state, you're at the same height. Well, of course, if you're at the same height, a ball is not going to roll. It's just going to stay where it is. Class is yours, my angels.